Okay, welcome everybody to section 2. Today we will start our discussion of univariate homotopy continuation. So we'll prove 3 fundamental properties of kind of our backup homotopy when all else fails. So you're going to see a lot of the themes in the course today in the univariate set. Okay, and then this section will last for 6 lectures, so 2 weeks. This Thursday, we'll implement some of the things we're discussing today, and Thursday. Okay, so the goal of univariate homotopy continuation in the polynomial setting, which is everything in this course, is to solve polynomial in one variable of degree b. Okay, so this is our usual form for a polynomial. We have some indexing set of monomials in this case, the numbers 0 through b, and we have coefficients, which we'll take to be anything in the complex numbers, but yeah. Complex numbers is fine, but I do want that the top coefficient is not 0. I really want this to be honest to goodness of degree d. But intermediary coefficients are fine with these. So that's the goal. Okay, so now I invite you to think for a couple of minutes on your own what it means to solve a univariate polynomial of degree d. So in math, we hear this word solve a lot, right? Solve for. What do we do?
We are looking for zeros of this polynomial, so factor it.
Indeed. Yeah, so we might want to factor it, right? Factor it over which field?
So since this is over C, we already have the fundamental theorem of algebra, so we know it can be factored. So we could factor it over C.
Indeed, it has some roots alpha I in C. We want to find them. Okay, so we push the goalpost. What does it mean to find these alpha i's? We know they might not be rational, for example. That's okay, so we solved quadratic equations in one variable. We might have some other exact representation in terms of additions, subtractions, multiplications, divisions, and taking out roots. If you've taken a field theory or Galois theory class, you know that even a representation of that form may not be possible, right? This is the Abel-Ruffini theory. So what do you want to solve? What could you? I give you some degree 5 polynomial with random complex coefficients.
F of alpha is as close to 0 as possible because it's numerical.
Yeah. This is a good place to start. We might want to find some complex numbers which we can write down, where when we plug them into F, we get some small number F, right? If you think about this a little bit harder and you're holding your feet to the fire, you'll realize that this isn't particularly satisfying either, because scaling this polynomial isn't going to change at 0, so it really doesn't change the problem, but it absolutely changes this criterion in which we consider things to be good, right? Because I could multiply this whole polynomial by 1 over a billion, and now whatever tolerance I was using, I'm probably everything looks like a root.
Yes.
You know, so that's not particularly satisfying. For today, we are going to lift ourselves the restrictions and the burden of actually answering this question rigorously. That's actually for the last section of this course. But I want to plant the seed that we should be a little suspicious. Okay. For us, amongst friends, we want numerical approximations of the alphas. So what do we want? Alpha is like, for example, something like 0.21134 plus the imaginary number, so square root of -1 times some other floating point number. So some decimal expansion. Up to some number of significant digits, and of course, the more the better in many instances. Okay, so that's what we mean by solve, and that's the goal of home continuation. Get good approximations of the roots of a univariate polynomial, where good is totally being swept under the rug. Okay. Go. Right, so some definitions and lemmas that we may recognize from previous courses. So a complex number is a root or 0 of f if f of a is 0. We have a root of f if and only if polynomial x minus a divides f. Right? But there's kind of a souped up version of being a root, which is being a root with multiplicity. Sorry?
I think that would be a comment there.
Ah, we have common. Yeah. Thank you, Deepak. Find the roots. Yeah, for sure. Thank you, Isma. All right, so complex numbers are root of f of multiplicity k. If, so my definition is x minus a to the k divides f, but x minus a to the k plus 1 does not divide f. Not only is there one factor of x minus a in f, but there's actually k of that. Okay. Another little note. You have a root of multiplicity k if you have a root of the first k minus 1 derivatives and the original column. A root of multiplicity 1 is called a simple root. Otherwise, it's called Okay, we've already heard somebody mention it, but there's the fundamental theorem of algebra. So I'll give one version. Polynomial of degree d has d roots over the complex numbers, counting multiples. If you have a root of multiplicity 3, that counts for 3 roots. Here. A lot of what makes the algorithms in this course work is this fundamental theorem. And we will see some of that today. So now I'll describe the setup of homotopic continuation. I'll describe just what the general idea is. I know I've already discussed this a little bit in previous classes. And then we will establish 3 really important properties of the homotopy we cook up, which will enable us to actually solve this f of x on a computer. So f of x for this whole course is the same thing. It's just some random polynomial of degree d in one variable that you want to solve. The idea solve f. First, solve an easy version of f and deform the solutions. Here we have f of x equals 0. And there are some d solutions in the complex part. If I can imagine these d dots living in a complex part. So we want to cook up the easiest polynomial of degree d possible to solve, which has some nice properties. And those nice properties will be that, well, 1, we know the solutions. 2, they're all distinct, so no multiple roots. And 3, they're like well spaced out in the complex plan. So I think we've seen before. 1 to solve here, it's x to the d minus 1. So this has d solutions. And they're called the roots of unity. So the ith solution is e to the 2 pi I over d times k. So times I, I guess. So it goes from 0 to d minus 1. Okay, form the vertices of a regular D-gon in the complex plane, centered at the origin, with one of those vertices being 1. Okay. So now we have the Mach system, which looks a lot like our f of x, but isn't. And we can write down those solutions. And indeed, we can find floating point approximations for the real and imaginary parts of these complex numbers. Now we got to connect things. So how do we want to connect things? So think of t, we're going to introduce this parameter t. Think of it like time, if you'd like. And at time 1, we're going to look like g of x, and at time 0, we're going to look like f of x. Maybe we can have a conversation later about why we're going from 1 to 0 and not 0 to 1, which might feel more natural for people. There's actually a good reason. It's not an arbitrary decision. All right, I'll just write it down. We've already seen. It is this convex combination of the two polynomials we're interested in. Verify that when t is 1, we are at g of x. And when t is 0, we are at f of x. Now the picture we want to imagine is that we have these nice smooth paths. These solutions to the d points we want to solve. None of them ever cross. None of them are going off to infinity. And so we've made this function from these so-called start solutions of our start system to the target solutions of our targets. But as written, those nice properties don't hold in general. So it is entirely plausible that you have the following issues. So you might have a priori that two paths are crossing. That's bad. You also might have that some solution flies off to infinity and then comes right back down, like that. That's bad. So that's bad thing number 2. Bad thing number 1. Bad thing number 2. You can have that behavior at the end. That's bad thing number 3. Or you could have this crossing behavior at the end. That's bad thing number 4. 1, 2, and 3 aren't going to happen after a mild massaging of this homotopy. 4, you're not going to be able to avoid. In fact, we'll see that if you're trying to solve a polynomial which has a multiple root of order k, then k of these paths are going to go to that. Okay. So when you think of one solution as really k copies of a solution, that's really the right way to think about it in terms of this. You're really seeing those k solutions all go to the same place. So all the properties I just mentioned are sometimes summarized. I mean, they're classically summarized as these these three adjectives. So first one's triviality. The start system is easy to solve, trivial. So you just write down the solutions. Second is smoothness. But these paths are smooth, they don't cross, they don't go up to infinity. And accessibility. All target solutions may be accessed via one of these paths.
One of them. Just by one path, you should be able to access all.
Sorry, for every target solution, there exists a path starting at some start solution, which goes there.
Yes.
Right? I'm not going to run this and only find half of my solutions. I'm going to find them all. Okay, so these are the three adjectives. How are we doing on time? We got the time. Okay, so what we're gonna need first is a little lemma that says, in this open interval, sorry, no. I'll just write it. Lemma. There are finitely many t-values for which has a multiple root. This is in C. There are finitely many t-values where if we plug t in, we get some polynomial in one variable, and that polynomial has multiple roots. Okay. Oh, so now this is done in detail in the notes that are on the website. I'll summarize it, try to go through it quickly. It's not particularly interesting. There are slicker proofs if you know the theory of resultance. For example, if you do know resultance, then you know that those t-values are, so they're exactly the places where the polynomial and the derivative vanish, right? And so you can write that condition as a polynomial equation in the t's using resultance. So you have some polynomial in one variable, t, and it has finitely many roots in C. So that's the resultance argument. But here's like a really, really close to the ground argument. Okay, so we're gonna bust up the possibilities into three types. First type is that x star, t star is a multiple root, and f of x star is g of x star, but that value is not 0. Okay, so let's evaluate this homotopy at x star. And we see that, so if f of x star is equal to g of x star, then we can just replace g of x star with f of x star. And we actually get that this is just f of x star, regardless of the t value. In other words, if the start system has a common solution with the target system, there's some solution which is invariant under the nodes. We're interested. Okay. Okay, so what did I just say? This is. Oh, wait, but this is not 0. So it actually can't be a solution. Yeah, sorry. So this constant root situation is actually type 2, not type 1. Type 1 is when it's not equal to 0. Type 2 is one indices. That was a comment, because we're assuming this is a root. So type 2 is we do have a common solution. In that case, we can actually factor out that term from the home tool. So every term in it has it as a factor. Right? You have a root if and only if you have x minus that thing as a factor. So if it's a factor of both terms, I can pull it off. Okay. Great. And now if this thing is, okay, so now we want to know, could this be a multiple root? So so x star would be a multiple root here if it was also a root of this factor for some t. Right? So you can actually write down the t value. This is linear. So you can write down the t value, which has x star as a root. The right-hand side has x star as a root when t star is this f hat over f hat minus g. Okay. But the denominator cannot vanish since x star does not have a multiple root. So we have cooked this up to already not have multiple roots. And so along the way, you don't get a multiple root. Okay. Type 3 is that f and g do not share the same value at t star. Type 3. X star is not equal to g of x star. Okay. So x star is a root for t star equaling, again, this, so you can solve for t in the homotopy after you plug in x star. Room. Great. So t equals f over f minus g, evaluated at x star. Okay. And so you can plug this into the derivative of the polynomial at this t value, and you can write down the expression, you get some rational function. The denominator doesn't vanish, it's f minus g, and they don't share the same value. But the numerator is some derivative of a polynomial, and so you can only have finitely many roots to a polynomial. So just to speed things along, it's all in the notes, right conditions for h prime, that's t star to be 0, and you get that this is the derivative of the product over this difference, and so this can only have finitely many solutions because that derivative only has finitely many roots because it's a polynomial. Okay, so not particularly illuminating as a technical result. Point is there are finitely many t values which give you a multiple root. And as a fundamental result, we need to move on and prove the accessibility result. Fun geometry fact. Fix a finite subset of the complex plane. And consider this is here. Consider all circles through the points 0 and 1. So for example, that's a circle. Keep on making this circle bigger until it starts to look just like that line segment. Circle look like that. But if you have a one-dimensional family of circles, does any 3 points determine a circle? How many of these circles go through one of the red axes? Yeah, if you fix a single red X, then these 3 points have a unique circle. So in the space of all circles through this point, all but finitely many of them will miss all of the X's. With the exception that maybe 0 or 1 is an X. Okay. But if you don't allow for that, then almost all circles will miss any finite set in the complex line.
Once again, could you go with this point just one more? Because why is it why are 0 and 1s
Again?
So why are 0s and 1s the points where this might not work?
So if 0 is in S, then there's no circle through 0 and 1, which doesn't go through something in S.
Yes. Okay.
So that's, but if that's not happening, then all of these circles will completely miss the finite set. So just to be very specific, fix a finite set S not containing 0 or 1, then all, namely infinitely many, circles through 0 and 1 miss S with only finitely many exceptions. Okay. So the set of all circles going through 0 and 1, that's an infinite set. If you look at the subset that go through something in X, that's a finite set. All right, so moving on. Most circles avoid a finite set. The finite set we're interested in is the set of t values for which we have a multiple root. Because what we're going to do is we are going to adapt this homotopy. So instead of taking the path from 1 to 0, we will go along one of these circular paths. Okay. And since almost all of these circular paths will miss the t values for which we have multiple roots, we'll show that no point along that path corresponds to a polynomial system with a multiple root. Because what we're really worried about when we cook this thing up is that one of the t values with a multiple root lives on the segment between 0. That's what can go wrong. pick some complex number on the complex unit circle. And look at the following path. So we're going to parameterize this path by the unit interval. It goes to C. And T goes to T gamma over T gamma plus 1 minus T. This is tau gamma. For which gamma? This is some angle on the unit circle, and I think it's negative gamma. Is that it? So that's something one can verify. I may be off by a sign. But you look at the real and the imaginary part of this, and you show that gives you a circle. Okay. So these are the paths we're going to take. So corollary to the fact that there are only finitely many t-values here over the complex number, which have multiple roots, and the fact that almost all circular arcs miss a finite set of points, and the fact that this is what those circular arcs look like, we have the better result of the day. F be a degree D polynomial with complex numbers of one variable, and G be x to the D minus 1. For all but finitely many gamma, so complex angles gamma, following homotopy has no multiple roots or any t value in this half open half closed interval. Can't control anything about the equals, but we can void the roots. Now what's the proof? The proof is that up to some constant c, this is the same thing. Okay, so sorry, let me give this a squiggle to distinguish it from this h. And then I want to write this as, yeah. So we take the usual homotopy we had. Instead of looking at the path from 1 to 0, we parameterize a new path from 1 to 0, called tau gamma. And we compose the homotopy with that. Okay, we're still going from 1 to 0, we're just going a different path in the complex plane. A path that misses all of the bad t values in the complex plane, almost surely. Okay. This result is called the gamma trick. And without it, you are doomed to the possibility that there's some t value in the unit interval which has a solution with multiple roots, and you get a path cross. Okay, so 1 doesn't happen if you make this adjustment. All you gotta do is stick a random complex. And so we'll see this in action on Thursday. Okay, I would usually stop right now, but I do want to finish off one smaller result, which is that 2 doesn't happen. So when would 2 happen?
You mean a pole or some sort?
Sure, a pole of maybe some function from the t's to f.
Assuming this is all algebraic.
Yeah. Another way to think of it is that it's when the leading term of this homotopy vanishes. For example, let's say I want to solve a quadratic equation, but instead of using a start solution x squared minus 1, I use x cubed minus 1. So now I got 3 solutions going toward 2 solutions. Well, what happens when t gets very, very, very small is this leading term, the term of x cubed, is going to 0 because I end up at x squared, right? So
Yes.
that's where a point goes off to infinity. Okay. So the other result that I'd like to say, which tells us that number 2 cannot happen, is the result that the leading term of this is not 0 for any t value between 0 and 1. So you can just write down what this leading term is. So we start at next to the d, we end at next to d, so there's definitely an x to the d here, and then what to be k. So this is negative cd, that's the leading coefficient of f. Right. Over. Sorry. It is cd plus t gamma minus c. Okay. So this is going to vanish. At t equals negative cd over gamma minus cd, which is equal to gamma over negative cd plus 1 multiplicative inverse. Okay, fine, whatever. The thing we want to show is that this is not a real number between 0 and 1. With probability 1, if you've chosen gamma to just be some random complex numbers, this isn't going to be a real number at all. Right? You would need these two complex numbers to have opposite angles so that they would cancel out. And you get something here. Right? So the probability 1, this thing is not real, and this is the unique t-value which gives this deviation. So it's certainly not happening between 0 and 1 if you've chosen a random case. Okay, so that doesn't happen, that doesn't happen. Why doesn't this happen? We've already discussed that going to infinity means the lead term is going away. That's only happening at one value, and it's certainly not at t equals 0 if we have chosen random gamma. So if it doesn't happen, 4, you cannot. 4 will happen, and there are ways to handle it, but we'll talk about that next week. Next class, what we'll talk about is that this picture starting here is really accurate, that these are really curves. They're not just like some random splattering of points, right? There's continuous movement of the roots. We're basically just going to apply the implicit function theorem over and over again to get well-defined paths here. All right. And then we're going to use some sort of pigeonhole principle that says for almost all t values, you have exactly d roots, and they're bounded away from each other. So at the end, you have to have d distinct roots. Okay, I have d distinct roots of some polynomial f. Well, they have to be the ones I'm looking for. The polynomial f only has d distinct roots. Right. Okay, and that will be the class on Thursday. Hopefully, we can get to coding how to follow these paths numerically in Julia. Okay, great. Thank you very much. I will pause the recording. I will take questions.